just when you thought it was safe to draw a Lewis dot structure and call it a day, now we have to think about resonance structures. Are there other valid Lewis dot structures? To figure this out, we can see if we can use electron movement arrows to create other Lewis dot structures where all the atoms still have an octet and there's still the right number of electrons. So for this example, we might want to move electrons away from the negative charge here. That would form a double bond. Then the nitrogen would have too many bonds. It would want to give up one. And the result would be this. So these are two valid Lewis dot structures of one molecule. The molecule is basically a hybrid of both of these. So there's a little bit of double bond here. It's actually 1.5-ish bond order. And a 1.5 bond order here. It's like halfway to being a double bond almost. And the negative charge is shared between the two oxygens. And there was a positive formal charge on the nitrogen the whole time, and that stays. Let's look at a few more examples. Look at this poor, miserable Lewis dot structure of this molecule here. With all its charges, even a carbocation, it must be very unstable. Let's help it find a more stable resonance structure by moving electrons away from the negative charge toward the positive charge. Step one might be to do this and form a double bond. Then this carbon would have too many bonds and it would want to get rid of one, and these electrons could migrate all the way over here, and the result would be good. By using electron arrows to move electrons from negative to positive charge, we found a structure with no formal charges. Benzene is the most famous example of a molecule that is stabilized by resonance. If we draw electron movement arrows to find another valid resonance structure, we the first step is to form a double bond here. Then this carbon wants to get rid of a bond, and that forms a double bond here. Then this carbon wants to get rid of a bond, and we come all the way around the loop, and we've made this resonance structure. The scientist Kekule figured out the structure of benzene. He had a dream that a snake was eating its tail, and he realized that this molecule was a ring shape. And since the actual molecule is a combination of both resonance structures, benzene has each carbon-carbon bond with 1.5 bond order, and is also often written like this. Okay, the trick to finding which is more stable is to find which one has resonance structures that stabilize it. If there are resonance structures that distribute the charge between multiple carbons, that means each carbon can have less of a charge, and that makes the molecule more stable. So let's see what we can do here. I'm seeing on the right that we can move 2 electrons from this double bond to be making a double bond here, and there's usually a positive charge that shows up when we move electrons away from a carbon. By the way, when doing resonance structures, most atoms follow the octet rule, except carbon. Sometimes you can make carbocations, and the carbon only has 6 electrons. It's weird. But other atoms have to have 8. But anyway, what we've shown here is that the molecule on the right has these 2 resonance structures, which means the positive charge is distributed between this carbon and the carbon on the end. Can the molecule on the left do this? This carbon is just too far away. We can try to get there, but we just make more trouble. We end up with a pentavalent carbon here. That's a big no-no. We never want to have carbons with 5 bonds. Remember, there's actually 2 hydrogens here too. so that's no good. There's no resonance stabilization for the one on the left. And let's look at the one on the right again. We even have another resonance structure that distributes positive charge to the carbon on the right over here. So we have a total of these 3 resonance structures. For our final example, we are given the question, the task of finding which is the strongest acid here. So again, we're going to use resonance. But here's the central concept behind this question. It's basically to find the most stable conjugate base. So what happens when these act as an acid? There is an acidic hydrogen which dissociates to form H+. And here's what this would look like. The hydrogen would come off and leave its electrons that it was sharing with oxygen behind on the oxygen. And this would leave a negative formally charged oxygen. And in this molecule, this is not going to be our winner because there are no resonance structures we can make here. So there's no other atoms that are going to share this negative charge with oxygen. Oxygen has to bear the burden of this negative charge all on its own. You don't believe me? You think we can make resonance structures? Fine, I'll try. We're going to do an electron movement arrow from negative charge, but oh god, that's making a double bond here. This carbon is going to have 5 bonds. It needs to get rid of one. The only thing it can do is ditch this bond. And oh man, that broke the entire molecule apart. We just tore the molecule in 2. We can't do that. Okay, so we succeeded in giving the charge to another carbon, but we're not allowed to break our molecule in half like that. So, moral of the story, this molecule on the left doesn't have any resonance structures, so it's not going to have a very stable conjugate base. You know, this is the conjugate base. Alcohols aren't generally very strong acids. So let's look at the second molecule, the one in the middle here. There's a double bond here. Usually exciting resonance stuff can happen when there's a double bond near an oxygen or a nitrogen. So this molecule is going to act as an acid and donate a proton. And we formed our conjugate base. So can we make a resonance structure here? Let's do an electron movement arrow from the negative charge. We're forming a double bond there. This carbon has to get rid of a bond, and here's a new thing. We can put these 2 electrons from that bond onto the carbon, and they can become a lone pair on the carbon. And what that's going to form is a carbanion. So the moral of this story is that the charge is shared both on the oxygen and on this carbon, and that makes this a very stable conjugate base, so it's more likely to donate a proton. Now let's look at the guy on the right, our last, final, third molecule here. Here's the conjugate base. Is the resonance? No, sorry. The double bond is too far away from the oxygen for it to help out. So, number 2 was the winner. The middle one is the strongest acid because it has the most stable conjugate base due to the multiple resonance structures.